Hello, welcome to this video. In this lesson we will learn how to use the most basic elements of ladder programming through their application in exercises. First, we will turn on an indicator light using a normally open push button, NO. If this application were done using only electrical wiring, the circuit would be very simple. You press the push button, the light turns on, you release the push button, and the light turns off. Now, we will do the same using a PLC. For such a basic application, it is not really necessary to use a PLC, but we use it as an example to understand the relationship between the electrical circuit and the programming logic. In this case, the push button is connected as a digital input and the light as a digital output. This wiring diagram may vary depending on the PLC model, but it serves as a reference for many commercial devices. Regarding the program, the logic is practically the same as the electrical circuit, only represented horizontally, as if we rotated it 90 degrees. The normally open program contact corresponds to the physical push button, and the coil represents the indicator light. The operation is straightforward. As long as you keep the push button pressed, the light will turn on. When you release it, the light will turn off. As a second example, we will see how to turn a light on and off using two push buttons, one normally open for start and one normally closed for stop. This circuit can also be made solely with wired logic using a relay to achieve self-holding. The electrical diagram would look like this. If you wanted to implement exactly the same thing with a PLC, the push button signals would be connected to the digital inputs and the light to a digital output, as shown in this second electrical diagram. The only difference is that the latching will now be done through programming. In the control program, the logic is basically the same as in the wired circuit, but represented horizontally. The operation is simple. When the start push button is pressed, the light must turn on and remain on even after the button is released. The light will only turn off when the stop push button is pressed. The instructions or blocks we use in the control program may vary slightly, but the final operation will be exactly the same. For example, besides using contacts and coils to create the latching, we can also implement this application using set and reset coils within the program. In both cases, the logic performs the same function: turn the light on when start is pressed, and turn it off when stop is pressed. Now we will see a very common example, turning a light on or off from two different locations within the same area. If we implement this application using only wired logic, we would need two SPDT switches, as shown in this circuit. If instead we use a PLC, it is no longer necessary to use switching-type electrical devices. Two simple push buttons or switches connected to the PLC digital inputs are enough, plus one digital output for the light, as shown in this second electrical diagram. In the control program, considering these two switches as inputs, we can implement the solution with two parallel branches, an open contact associated with the first switch in series with a closed contact associated with the second, and the second branch configured similarly. The operation is as follows. When the first switch is actuated, the light turns on. If from the other location the second switch is actuated, the light turns off. Then, if we return the first switch to its initial state while the second remains actuated, the light turns on again. This behavior perfectly emulates what happens with traditional SPDT switch wiring, but in this case the logic is executed inside the PLC, which allows you to add more conditions or additional functions if necessary. Although in practice this application is usually solved with wiring only, it serves as an excellent example to understand how to program this type of functionality in a PLC. In this exercise we will see a simple application to select small boxes and large boxes on a conveyor belt. The system has a start/stop control station, a conveyor where the boxes travel, 2 proximity sensors that detect the type of box, and a push cylinder responsible for diverting small boxes to the side. At the bottom you can see the devices used. In the electrical diagram, the connections of the push buttons and sensors to the PLC are shown, as well as the outputs that activate the conveyor motor and the push cylinder. In the control program we consider 2 main parts. The first is the start/stop logic of the system. When start is pressed, the conveyor motor begins to run and the system is ready to sort boxes. When stop is pressed, the conveyor stops and the cylinder returns to its initial position. The second part is the logic that activates the push cylinder. Now let's look at the operation. When the system is running and a large box passes by, the sensors detect its presence, but the cylinder does not actuate, it simply allows the box to pass. In contrast, when a small box passes, only sensor S3 detects it. If the system is on, S3 is active, and S4 detects nothing, the PLC commands the cylinder to push the box to the side of the conveyor. Then the cylinder retracts and the process continues. Timers, counters, or other functions can be added to this logic, but we will cover those in later lessons. Let's review some contact logic in ladder, which works very similarly to the behavior of real electrical contacts. When we place contacts in series in a program and they are associated with digital inputs, their operation depends directly on the state of the PLC's physical inputs. For example, here we see 3 normally open contacts in series. If only one of the associated inputs is activated, output Y1 does not change because all 3 inputs must be activated at the same time. This represents a logical and function. The table below clearly shows that the only combination that produces a 1 on the output is when all 3 variables, var1, var2, and var3, are 1. If even one of them is 0, the output will also be 0. Now let's look at a similar case but using 3 normally closed contacts in series. In this case, at the beginning all contacts are closed and output Y2 remains active. But if one of the physical inputs associated with these variables is activated, that contact changes from closed to open and the output immediately goes to 0. When working with contacts in parallel, the behavior changes from the previous examples. If we place 3 normally open contacts in parallel, each associated with a digital PLC input, just one input needs to be activated for output Y1 to also activate. This corresponds to a logical or function. The table below shows that the only way to keep the output OFF is when all inputs are deactivated. Any other combination, even a single input at 1, will cause the output to be active. Now let's look at the case of normally closed contacts in parallel. In this condition, output Y2 will remain active as long as at least one contact stays closed. The only way to turn the output OFF is to activate both inputs associated with these contacts simultaneously, which will open both and deactivate Y2. In any other case, the output remains on. Finally, let's see some combinations between open and closed contacts, placed both in series and in parallel. All these variables are associated with PLC digital inputs, so their behavior depends directly on the state of those field devices. Here we can see another section with different combinations of contacts. Depending on how the inputs are activated, the logic will or will not allow current flow toward the corresponding coil. And to finish, we see an example where 2 coils are activated at the same time. These coils do not necessarily represent physical outputs, they can also be internal memory bits that are then used in another part of the program to continue a sequence or generate new control conditions.